Good afternoon, everyone. My name is Andy Xiao. I'm a postdoc at Cooperative Institute for Limnology and Ecosystem Research at University of Michigan. I'm so delighted to be here today and to have the chance to introduce our Great Lakes Seminar Series speaker, Dr. Andre Erler. Dr. Erler is a climate scientist at Aquanti, a hydrological science and research spin-off company of the University of Waterloo in Canada. He got his master's degree in meteorology from the University of Mainz in Germany in 2008, and his PhD in physics from the University of Toronto in 2015. Then he joined Aquanti to continue his postdoctoral research. He is now working on the topic of climate change impact on the weather resource and agriculture in Canada. He is skilled in numerical modeling, high-performance computing, and programming, especially Python. In this seminar, he will present high-resolution, dynamically downscaled climate projections for the Great Lakes region using a coupled WRF FLake model. Thanks to the Great Lakes Seminar Community and Erler for supporting this event. Without further ado, please join me in welcoming Dr. Andre Erler.
Yeah, thank you very much, Andy. It's a pleasure to be here today. And yeah, I'll just start. This is the logo of my company, Aquanti. We're actually a very small hydrological consulting modeling company. And yeah, mostly actually academic researchers from the University of Waterloo. And mostly hydrologists. Now we are going more into climate. I'm the first climate scientist I hired. So I'm mostly be talking about regional climate modeling, and that's also what I did for my PhD that I did with Gula Peltier in Toronto. And for my PhD work, I focused on Western Canada, but now I'm working on the Great Lakes region. And regional climate modeling or dynamical downscaling has basically the goal of providing climate projections that are on a scale that is relevant for impact modeling or climate policy. And most people would probably agree that hydrological impact of climate change are the most relevant now, and that's what I'm mostly talking about. Here's a brief overview of my talk. First, I'll sort of introduce dynamical downscaling, regional climate modeling, and the experimental setup. Then I'll show you projections based on the dynamically downscaled simulations that we've done for the Great Lakes region for basically temperature and precipitation, like the main climate variables. And then in the main part of the talk, I'll talk about the implications for the hydrological cycle and how, for example, runoff might change. And before I get into a short description of changes to precipitation extremes, maybe possibility for drought, and then a little bit about the lakes and how the climate change actually might affect the lakes. But this is really based on the lake model in WRF that we use, and I'll tell you a bit about that. And I have the hope that maybe some of you would have some insights into some of what I will show here, because I don't understand all of what's happening there. So now, introduction. The dynamical downscaling is supposed to do statistical downscaling. You take a GCM, you're trying to get high resolution information for particular regions from that GCM, and you can either do this with statistical methods, or you can take, for example, a high resolution weather prediction model in a limited area, force it with the GCM boundary conditions, and then get the high resolution output from this weather model. And this is basically the route that we have chosen. That's called dynamical downscaling. Dynamical because it's dynamically or physically consistent. And the models that we use is CESM, the Community Earth System model from NCAR, as the global model, and WRF, the Weather Research and Forecasting model that Andy is also using here, as the regional model for high resolution. CSM is a GCM with a resolution of about 1 degree, whereas we run WRF at 30 kilometer in the outer domain. The outer domain looks about like this over North America, and then we have another inner domain with 10 kilometer resolution. This is a map of the outer domain. It's very similar to the NAR projection, if you're familiar with that. It's essentially identical. And here are the Great Lakes. And in CSM and in many other GCMs, the Great Lakes are essentially non-existent, even though they may have some lake parameterization, but there's very little effect on it. And in a regional model, you actually have a lot of grid points that represent the lakes, so there is a potential to have a strong lake effect in the regional model. However, until recently, and Andy has also struggled with this problem, WRF actually did not have any particular treatment of lakes. It was just sea surface, and you would have to prescribe temperature. But we've solved this problem. And by coupling a simple column lake model to WRF. And this is actually not what I have done. A postdoc in our group, Jonathan Gula, has done this mainly in 2012, so it's actually a while ago. Here's the outline of the inner domain that we use. So it's mostly Ontario and the Great Lakes region, and we are also here in this part. So the experimental setup, meaning what time slices we run. The global model, of course, runs from pre-industrial to end of century, like 2100, continuously. The regional model is very expensive to run, so we don't run this for the entire time. We choose time slices to downscale, and this is a historical time slice, a mid-century time slice, and an end-century time slice. And these are all 15 years. Now, 15 years are on regional scales not really enough to deal with natural variability. So there's just too much random variation, and that's why we run 4 independent initial condition ensemble members, so with the global model, and then downscale them individually, so that we end up having 4 ensemble members for every period, making a total of 60 years for our climatology for every period. And so this is to beat down natural variability. I will mainly be talking about the end-century results, not so much about the mid-century results. And we have used RCP 8.5 only to essentially get the strongest signal. That's also why we focus on end-century. There are 2 different configurations for WRF that we use, that is to estimate or assess how much sensitivity there is to model configuration, or what the model uncertainty is. And this turns out to be actually really important, and is also the subtitle of my talk, which was initially not intended. So it turns out there's a lot of differences between these 2 configurations. That's quite interesting. And yeah, so I've already said the initial condition ensemble was 4 members. These are the 2 WRF configurations that I'll be using, and one will be denoted as the G configuration and the other one as the T configuration. This is mainly to be consistent with one of our first papers on this matter that was written by my colleague Mark Dorgewell. And WRF G will be the main configuration that I'll be talking about, and then I'll always at the end compare it to the T configuration. And the main differences between these are moist physics. So the G configuration uses a 2-moment microphysics scheme. So that means it has a better representation of the distribution of cloud droplets. And it has an ensemble cumulus scheme, so a more advanced cumulus scheme. Whereas the T configuration has the default single-moment microphysics that just assumes a uniform distribution, or a fixed distribution, I should say, and the Kind-Fritsch cumulus scheme, which is also the default in WRF. For both, we use the same radiation scheme, RRTMG, which we found to be the best. We use a NOAA land surface scheme, if you're familiar with that, and both have the FLake lake model. So FLake stands for freshwater lake. And I'll say a bit more about FLake when I get to the lake temperatures. Okay, but now first for the climate. And before we go to the projections, just a brief overview of what the climatology looks like. And I'm sure a lot of you are actually already familiar with this, but just to go over it. Here's the Great Lakes Basin, and there's a strong precipitation gradient. This is annual precipitation from GPCC at a 1/4 degree resolution. So there's a lot more precipitation in the south and at the coast. That's also where the moisture sources are, the moisture coming in from the Gulf and also from the Atlantic. Especially in the winter, this gradient is very pronounced. In summer, it's less so. In summer, there's more precipitation also in the northwest. And one thing that I want to point out here is there's noticeable lake effect snow, and this is, of course, also something that people here work on. It's very noticeable in the lee of Superior, but also in the other lakes. If you see how this is represented in the models, here is CESM. This is, again, the observations. This is WRF at 30 kilometers, and this is the NAR reanalysis, again, annual average. And you see that in CSM, there's essentially no trace of the lakes in the precipitation field. Even though CSM actually does have a lake model, it doesn't seem to have very much effect. Whereas in WRF, the rain belts in the lee of the lakes are very prominent, actually overestimated. Whereas NAR actually has a lot of strange artifacts along the border, which have to do with inconsistent data assimilation. I'm sure some of you have already seen this. NAR is a bit famous for this. So yeah, despite actually having a lake model, CSM does not really show any lake effect. And this is probably because of the low resolution, maybe also because the lake model is not configured correctly. But I don't know, actually. I'm not an expert on CSM. So for the projection part now, this is temperature projection, fairly straightforward. There is warming. Here in the top is summer, in the bottom is winter. On the left side is the G configuration, on the right side is the T configuration. So in winter, there's strong polar amplification that is expected, and it's pretty consistent between both of the models. In summer, there's higher warming over the lakes, and this is something I don't fully understand yet. I'll get back to that. But there's also more warming in the T configuration than in the G configuration. And if you look at CSM, this is even worse. CSM has even more warming in summer. For the precipitation field, again, the winter is fairly consistent, but in summer there's a difference. And this time it's even the opposite sign. So T configuration gives less precipitation in summer, whereas the G configuration gives more precipitation. And if you look at CSM, CSM shows even more decrease than the T configuration. So these three models basically span the entire range of possibilities that you could think of. This is kind of discouraging. It means there's basically very low prediction confidence for summer precipitation, whereas for winter, they're all consistent. So this difference between WRF and CSM, and even between different WRF configurations, is quite striking. And this mostly has to do with, I think, with energy balance on the surface. Now, briefly for validation, this is now validation for historical period precipitation. One interesting thing to note is that T configuration actually has, even though it shows a decrease in precipitation in the future, in the historical period it actually has a very large positive bias. So it's not really dry. In the historical period it has too much and then it decreases a little bit. Actually at the end of century it has similar precipitation amount as the G configuration. Whereas the biases in winter are relatively similar in the precipitation field. One interesting thing to note is, I've so far shown you the outer domain at 30 kilometers. This is the inner domain at 10 kilometers. The biases are very similar. They're even a little bit stronger at the 10 kilometers. So there is not very much difference between 30 kilometer and 10 kilometer, I have to admit. You could even say that 30 kilometer is a bit better because the biases are somewhat smaller. And in the climate change signal, precipitation change or temperature change, there is no difference between inner and outer domain. So resolution doesn't seem to affect it anymore. which also begs the question whether the difference between WRF and CSM is mainly because of the resolution or mainly because of the physics. Okay, so now temperature here, there are again in summer large differences. The T configuration is hotter than the G configuration. And now this is interesting because unlike precipitation, G configuration is hotter in the historical period, but it also warms more. And this is even more so the case for CSM. CSM has a very large warm bias and then even more warming. And in winter, the G configuration is a bit better, which I suspect is because of the microphysics and the resultant cloud cover. And actually in summer, I suspect there's also a role of cloud cover and radiation. I'll get to that. One thing I have to say, and this is the red box here, I'm not showing spring, but in spring, both configurations have an extremely large negative bias because the snow does not melt quickly enough. And this is likely because the snow model in NOAA does not account for snow aging, and so the snow albedo remains too high throughout the winter. And this is much better with NOAA MP with a newer snow model. Okay. So now I can get to the hydrological changes. And whoop, this is going in the wrong direction. Okay, good. So hydrological changes. So now I'm going to show a lot of plots where I'm averaging over the entire basin, which is the area that's outlined here. There should be something. Right, okay. The area that's outlined here in white. So these are areas over the entire basin and over the entire 60 years of ensemble for each period. Yeah? Okay, and so these plots basically look like this. There's a seasonal cycle here, then there are monthly values, and the annual average is here on the right, just for information. And then some quantity, most of the time water flux is on the y-axis. Observations are always in dots. And model values are always in lines. And these bands around them are the 95% confidence intervals based on the standard error of the mean, based on natural variability. So if it's outside of the confidence intervals, then it means it's statistically significantly different. For example, we have a statistically significant difference to observations in spring and summer in precipitation. So variables are always color-coded. Precipitation is green here. Snow is blue. And obviously snow in winter. Precipitation peaks in summer. And red is net precipitation. So net precipitation is precipitation minus evaporation. So it's sort of the water input. Yeah? And that peaks in spring, because then it's cold enough that evaporation is not too high, but there's already a lot of precip. In summer, precipitation is high, but evaporation is also very high. Okay? So precipitation maximum is in summer. And snowmelt maximum would also be in spring. Okay, so now we're looking at climate change. We're marching this into the future. The dashed line now is historical, and then the solid line is at this point mid-century, and now it's end century. Yeah? So there's a large increase in precipitation in summer, especially in summer, but also in winter. And as a consequence, also an increase in net precipitation. So in this case, the increase in precipitation actually outpaces the increase in evaporation. And obviously a decrease in snow, that's not very surprising. But if we go to the T configuration, and this is this now, we see that the picture looks a bit different. So the precipitation was high to begin with, and then it goes down a bit in the summer. But actually you can see this reduction in summer is actually more a shift earlier into the year. And net precipitation actually becomes negative. So in this case, evaporation outpaces the increase in precipitation. Yeah? And the important question now is, So here I've underlaid the G configuration in a transparent or in a lighter color here, so for direct comparison. So here, net precipitation in late summer, there's a huge difference, right? So the interesting question is, how does this affect the water balance, right? Runoff, for example, or soil moisture? So this is what I'm trying to show here. This time in red is evaporation, and the total water forcing is in blue. And the purple color is runoff. So total water forcing is snowmelt plus liquid precipitation minus evaporation. Okay? And we'll march this into the future again, like this. So evaporation increases, that's not surprising. In spring, there is not that much change. Snowmelt decreases, but precipitation increases. So compensating effect. But then, as might have been expected, because the water forcing increases, runoff in late summer in this configuration increases. But, as you might already suspect, in the T configuration, because of the massive decrease in water forcing, the stream flow actually decreases. So these are two opposite projections for late summer water availability, basically. So the question is, of course, which one is right, or can we prefer one over the other? And this is a difficult question. Then we would have to find a fault in one of the models. And we might just wonder, why does this happen this way? So a little bit more investigation. Why does G produce a cooler and wetter climate than T, right? And an interesting sort of related question, T has a higher surface temperature, but it also has much higher evaporation. So it means it actually has much higher latent heat cooling. So where's all this energy coming from? They both have the same radiation scheme. So they should have the same input from the sun, right? So if you have more evaporation, it should be cooler. Well, so I'll compare this to station observations with radiation, and this will shed some light on this. There's a research station that has a fairly comprehensive instrumentation north of Toronto, and this is at the moment the only data set I have for this, but this is already quite interesting. So this is now at this Aurora research station, G and T configuration again. Now the solid line is, this is just historical, this is temperature. Max temperature, mean temperature, and min temperature. So max and min are diurnal maximum min, max and min temperature. The solid line is T and the dashed line is G. And in summer, T is almost spot on, whereas G is way too cold. In winter, they are both too cold. And in spring, there's a huge bias here, as I've mentioned before. This is because of the snow model. But why is there this difference, right? So when you look at radiation, excuse me, yellow is total solar downwelling radiation and shortwave radiation, and red is the net radiation. And it's quite obvious that the T configuration gets a lot more energy from radiation, right? Even though they have the same radiation scheme. So this is it's maybe a bit strange. And then if you look at this, compared to observations, actually G is the one that's right. G has the correct radiation, whereas T has too much radiation. But T has the correct surface temperature, and G is too cold. So why is this? And I suspect the reason is that because we have a precipitation bias, we have too much precipitation, so we have too much evaporation. If you have the correct radiative forcing, you will have a too cool climate because of too much evaporation. The T configuration happens to have the correct surface temperature despite the high evaporation, but for the wrong reason, basically. It has two compensating biases. And the reason, so where this difference comes from, why one has more radiative forcing than the other one, I suspect that the reason is cloud cover, but I cannot prove this 100% at the moment. Yeah, but I think this is the most likely candidate. Okay. So much for the energy balance and so the difference between these two configurations. Now, a little bit about extremes. So 3 years ago, we had a big flood in Toronto. These are pictures. The subway flooded completely, and this was just from like a short-term heavy rainfall. And this is what this picture shows. And in the same year in Alberta also had a huge flood. So Canada had a significant flooding problem in 2013. More recently, it was more fire, but yeah. So is this a something that will be coming more often? And of course, one thing is to say we cannot really attribute particular events to climate change, yeah? But that's clear. So this is now a similar plot as before with precipitation changes. So G configuration left and T configuration right, and summer and winter. And for end of century, RCP 8.5 again. So G configuration shows a pretty consistent increase in precipitation extremes. And what I mean by precipitation extremes is for every season, we pick the meaning like the 3 summer months or the 3 winter months, we pick the day with the highest precipitation out of this season. So that's sort of the 99th percentile, or rather the highest out of 90 or 92 days. And then we average these maxima over all the 60 years in the period. Yeah? And then we see whether this increases or not, right? And in the G configuration, it increases by 25%. So it's a considerable increase in precipitation extremes. Huh? Whereas in the T configuration, there's some increase, also a little bit of decrease. Overall, there's a slight increase in the Great Lakes Basin. But it's not strong. Whereas in winter, in both cases, it increases. And one thing that is interesting to note here is that this pattern is very similar to the pattern in the means, except that the extremes increase a little bit more. And CESM, for example, just shows a slight decrease. That's a little bit less decrease than in the mean precipitation, but still a decrease because the mean decreases as well. So this is also something I've noticed in Western Canada when I looked at these data, that generally the changes in the extremes are actually pretty similar to the changes in the mean. Okay, so this is again averaged over the basin, and this is extreme precipitation, and this is convective precipitation. And then the brown line is a 5-day average extreme precipitation. So that's more for large-scale flooding. But it generally follows the daily extremes. It doesn't have such a strong seasonal cycle because in summer precipitation is a bit more intermittent. Yeah, and in summer convective extremes dominate. And if you go into the future, convective extremes increase, but total extremes increase as well. The increase in convective extremes tends to be a bit larger. But if you look at the T configuration, same thing as with the mean. There's basically this shift into earlier in the year. Yeah? So if you want to compare. So that's basically the broad strokes of the changes in the extremes. My colleague Mark Doigeville had a whole paper about changes in extremes at mid-century based on some of these simulations here. So he didn't have the 4 ensemble members. He only had 1 simulation at that point. He found that compared to station observations, the G configuration has the best performance. And he found that the increases are largely consistent with thermodynamic expectations, meaning about 7% per degree. He did find some evidence that the very extreme quantiles, so higher than 1%, maybe 0.1%, increase more than the sort of moderate extremes, which would be the 1 percentile. But the statistical significance of this is not very strong because we didn't have a lot of data here. So to first order, it still holds that the increases in the mean and the extremes are pretty similar. So we are currently working on a more comprehensive picture on this with extreme value analysis. And we've already published this for Western Canada. So now briefly on drought. This is again for the G configuration, and the G configuration tends to be relatively wet. So the green line is soil moisture, and this is relative soil moisture. So this means it's always around like 80%. Yeah? So fairly high soil moisture. And the purple line is latent heat flux, and the red line is sensible heat flux. So in summer, latent heat flux dominates. Huh? If we increase if we go into the future, mid-century and end-century, the latent heat flux increases the most. So basically, most of the increase is in latent heat flux. Sensible heat flux does not increase very much because the temperature gradient between ground and atmosphere doesn't increase that much. So all the radiative forcing is balanced by evaporation, basically. And because of the increase in precipitation, actually soil moisture increases in late summer in this configuration. But in the T configuration, the opposite is the case, as you might have expected. So evaporation is a lot higher, as you've already seen. There is actually an increase in sensible heat flux in late summer, and this can be seen as an indication for drought. So when sensible heat flux increases and latent heat flux decreases, and there's maybe some indication here. And the soil moisture here does actually go fairly low, like 40%. I would say though that it's still higher than in most parts of the prairies. So it's not super dry. But then again, also a lot of the prairies actually have irrigated agriculture. So it's something that's manageable, but if it turns out as in this configuration, then this might be something to consider for the future. But in the G configuration, it doesn't look like it. So now, yeah, now a little bit about lakes. And a little bit about FLake and its history in WRF as well. So Jonathan Gula initially used FLake to provide a more sensible bottom boundary condition for WRF. So previously, when you run WRF over a region with large lakes, what WRF would do is just interpolate sea surface temperatures to the lake locations. Or alternatively, you could just average the surface air temperature. And both of these are not really satisfactory solutions, especially interpolation of sea surface temperature when large water bodies are far away, and this can be very arbitrary. So what he did was he used FLake, this simple lake model, forced with a CSM input, and to estimate the actual lake temperatures for the Great Lakes. So he uses bathymetry from the Great Lakes, input from CSM or from CCSM3 at that time, then get a new lake temperature, and then force WRF at the bottom boundary with this new lake temperature. This is offline coupling. And this is what he published in 2012. And he found a significant reduction in ice cover over the lakes that might be expected, and a significant increase in lake effect precipitation, and also in snow, lake effect snow, despite the warming. Now, since then, Jonathan has actually coupled the FLake model online into WRF, and it's now in our version of WRF, it's running online and it interacts with the atmosphere. But originally, FLake was developed by the German Weather Service for their regional weather prediction model, Cosmo. And basically, the structure is it's a 1D column model. It has a mixed layer at the surface, and then a thermocline profile, which is based on some kind of self-similarity principle, similar to boundary layer theory, but I'm not very familiar with this. But it's basically just one profile that depends on a few parameters. And then there's the bottom sediment layer, which also has a similar self-similarity profile of temperature. So it essentially has only really three layers, but these two layers are pretty complex. And then there are also parameterizations or modules for radiation falling into the water and having sort of a volumetric heating effect. And then there's also lake ice and snow somehow represented in the model. So this runs in WRF. So now I'm showing here this is temperature again, but averaged only over the lakes. So this is all lakes all the lake surface averaged in WRF. And this is the surface air temperature. It's not the lake skin temperature. Right? So red is maximum, blue is minimum, and green is mean. The light color here is the temperature of the surrounding land, whereas the stronger colors are the actual lakes. Yeah? So obviously the diurnal cycle is much stronger over land, and it's muted over the lakes. And these triangles here, this is NAR. So this is the lake temperature from NAR. And compared to NAR, we can sort of see that, or also compared to the land, now the land is in red, it's not in green, so you can see it better. But this is the mean temperature, and green, this is still the mean temperature. I've removed the minimum and maxima, so that's not so messy. You can see that there's like a 1 or 2 months lag between the lake temperature and the temperature of the surrounding land, and that's maybe not surprising. That's not surprising, right? Now, if we go into the future, now the lakes actually seem to overtake the land, although at the end of century that's not the case anymore. But the increase in temperature is slightly higher over the lakes than over the surrounding land. So maybe half a degree or a degree. Yeah? I'm really not entirely sure why this is the case. Yeah? So I've looked a little bit at the heat fluxes, and maybe someone can also have some insights into this. Here's again heat flux in the strong lines are over the lakes, and then the weaker transparent lines are over the surrounding land. Yeah? So, oops. The purple line is latent heat flux as before, and the red line is sensible heat flux. And so at least in WRF coupled with FLake, latent heat flux is very strong in autumn, presumably because the atmosphere is cooling and getting drier, and the lakes are still warm and still have a lot of evaporation. Sensible heat flux is very high in winter. That's probably not surprising. But then if you go into the future, we notice two things. One is the sensible heat flux drops. That's probably because the atmosphere warms a lot in winter. So it does make sense. But the latent heat flux also drops a lot in late fall. And this is something I don't really understand. It increases in summer, presumably because of increased evaporation due to higher temperatures. That seems to make sense. I'm not sure about this part here. And if you look in the T configuration, basically the same thing happens, just at a higher level of latent heat flux or evaporation, right? But overall, a sensible heat flux decreases, and that makes sense. But the latent heat flux here increases, or in the G configuration doesn't change due to this decrease in fall. Yeah, so why is the latent heat flux decreasing? I don't know, but I'll just leave it at that. Okay, so this is basically my main points, summary of the results. This is to remind you that there's a large difference between these two simulations. One shows drying and one more stream flow. But one thing about, for summer, what we can say is there's a large range, but there might be an increase in extremes. So for winter, there's a consistent increase. And for the hydrological impact, as I said, there could be an increase in stream flow or a decrease. But it's possible that the main risk might actually be from increased flooding if the G configuration is right, because then that would actually mean quite a lot more water available. Okay, but yeah, keep the major differences in these configurations in mind. Yeah, thank you. And I want to briefly acknowledge some of my colleagues. Mark Deutschel has actually done some of these simulations and has a paper on the extremes I've mentioned. Jonas and Gula did most of the work with coupling of FLake. Feng Yise is a new student in our group. He's at the moment he doesn't do very much, but he's learning how to run WRF and doing some data shoveling. And Dick Peltier was my advisor at U of T, and he's basically sponsoring all of this work. And Akwanti gave me a day off to give this talk here. Okay. So, any questions?
precipitation pattern when you face issues related to drought?
That's an interesting question. So the question is shall I repeat it? Shall I repeat the question, or yeah? So the question is if there is a specific circulation pattern in the Great Lakes that is related to drought. And this is an interesting question that I've asked myself as well. We've done some preliminary analysis that would suggest that water availability or moisture flux is related to evaporation from the Great Lake, the Great Plains. So advection from the Great Plains would play a large role, and it seems that in some of the predictions, the lower tropospheric winds change to a more zonal direction so that there's less advection in the meridional direction. But this is very preliminary at this point. Yeah?
Two questions.
Mm-hmm.
One is in the comparison of the precipitation, I saw the model predict 2 months earlier in peak than the observation.
Mm-hmm.
And the other is when you use at the very beginning. And yeah, this one. You look at the peak,
Mm-hmm.
you can see about 2 months early.
Right.
And I wonder, these are persistent. I wonder this is because of the inner domain is so close to the Great Lakes, and then when you do the simulation, the boundary, I think the boundary effect can snare or spoil the model results or something.
Right. So the question is whether the fact that the precipitation in WRF occurs a little bit earlier in the year than in the observations might be related to a boundary effect. So if I remember correctly, this also happens in the outer domain. Although actually I have not recently looked at it, I might be wrong, but I think it also happens in the outer domain. I don't think that boundary effects between outer and inner domain are that strong. There are certainly boundary effects, but the update is very rapid. It's basically every time step from the outer domain. So that, yeah, I don't think the effect should be that strong. But yeah, so at the moment, I don't think that this is I think this is also the case in the outer domain. Yeah.
Even you update very, very fast, but the error accumulated at the boundary or happen or occur at the boundary will propagate into the...
Right. There are certainly artifacts at the boundary. That is certainly true, yes. And parts of the Great Lakes are close to the boundary, you could say, although most of them, the parts that are close are more, they're closer to the eastern boundary. So the inflow region should be better, but I share your concern about the boundaries. If I would do this again, I would make the inner domain a bit larger. Yeah, I agree with that.
Okay, I want to add something to John's question. Have you used spatial nudging in WRF?
The outer domain has a slight spectral nudging, yes. The inner domain doesn't have nudging, right? Yeah. But so the outer domain is actually pretty large, and so it actually has a fair degree of independence and also just mesoscale variability. Like if you rerun even with the same boundary forcing, you still get slightly different results, right? And we have, for example, one ensemble member where we had a mega drought at the end century, and then we ran the exact same forcing again if we didn't have the drought. So the mesoscale variability should not be underestimated. Yeah. No, yeah.
I was wondering why you found two cases, the outer domain and the inner domain, in the context the outer domain is very close to
Right.
I'm wondering why you run alpha domain instead of using NAR for the information.
Oh, so the reason why we don't use NAR is quite simply that we do projection. So NAR is only historical, right? You're right. The outer domain is. We've actually purposely made it almost identical to NAR, so as far as we could, so that we could do like a direct comparison with NAR. Yeah. Now, why we chose to do 2 domains? Initial tests seem to suggest that lake precipitation and lake effect is better at 10 kilometer, until we realized that we are probably overestimating the lake effect. Generally, as I said, with respect to climate change signals, there is really no difference between the inner and outer domain. So I think now, I'd say in retrospective, it would not be necessary to run the inner domain, and if I were doing more experiments, I might not run the inner domain. Actually, for physics sensitivity test, I probably wouldn't. It is good to have done it, because now I can say that it doesn't matter, and it's sort of like numerically converged, if you will, and until you get to the cloud resolving level, of course. But as long as you're using cumulus parameterizations, it seems that the inner domain at 10 kilometers is not really necessary. Mm-hmm.
So do you do the bias correction after you do the interpretation?
After we do what?
For future projections, you do a bias correction?
Oh, no, there's no bias correction involved here at all. Yeah, it would make sense, for example, to bias correct CESM before forcing WRF with it, because the climate you see, for example, when you force WRF with CSM and when you use, for example, ERA-interim reanalysis for forcing, is slightly different. So there are some biases from CSM that are inherited by WRF, but I would still say the differences between the 2 WRF configurations are still much larger. So I'd say the WRF makes more of its own climate. Mainly because the domain is so large. If you would choose a smaller domain, that would be much more important. Yeah. But yeah, so far we have not done any bias correction. We are now working on bias correction because we want to use this for hydrological modeling. And for hydrological modeling, if your surface climate is as far off as, like, for example, in the GOT configuration, right, where either we have far too much radiation or it's really too cold and wet, like this is a different type of climate. You need bias correction, otherwise you're going to get a completely different hydrology. Mm-hmm, Brent.
This one is from the webinar, and the original question is, could the decrease in latent heat flux be caused by a decrease in evaporation?
Well, that's what it means, yeah.
To clarify, you were pointing out something in the late fall that was...
Right. So what this refers to is yeah, in late fall, the latent heat flux decreases at end century, even though temperatures generally increase, right? And so, I mean, decrease in latent heat flux means decrease in evaporation, obviously. But yeah, what is the reason for this? I've looked into relative humidity, for example, above the lake and things like that. The saturation deficit actually also increases. So, and potential evaporation over the lake also increases. It does not decrease. So it's not that, it doesn't seem like evaporation is suppressed. So yeah, I'm not quite sure why this happens. I've looked into several options, and it all does not seem to make sense. Yeah, okay. Any more questions? Okay.
I guess this one will be from me. I was surprised when you were showing the annual cycle of latent and sensible heat flux over land, that was showing a drop-off in central heat flux quite early in the summer and a continuing rise in late heat flux, and I thought there would be more of a match between these.
Right. Yeah, here, like here, for example, right?
Right, yeah.
Yeah, so the question is, why does latent heat flux over land increase and sensible heat flux in late summer actually decrease? That's a good question. I'm also not entirely sure why this is, but the sensible heat flux depends on the difference between the surface and the air temperature, right? So it could just be that the air temperature increases. It could also be that just so the whole surface, boundary layer surface system moves to a higher temperature. The higher temperature tends to encourage more evaporation, and there tends to be a higher saturation deficit. So that there's more that can be done by evaporation maybe, whereas earlier in the year the air is still too cool to evaporate that much. That's just a guess at the moment. But yeah, you're right. I would have expected them to be more symmetric as well. Yeah. Yeah. Okay.
Okay. Thank you, Dr.